Here's the second day of 10.1 sample spaces and probability, keeping in mind the essential question of how can you list the possible outcomes in the sample space of an experiment. So we're starting today off with example 4. And we are given a dartboard. So it says you throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points? So what we want to do is we want to find the probability of 10 points. So notice that the 10 points is coming from this circle here. So just to let you know, the area of a circle is pi r squared, so of a circle, and the area, of a square is base times height. Okay, so we're going to have to obviously use that in this picture here. So the area of this circle is going to be the probability we want to find, but the total outcome is the board itself. So this is the total. The circle is what you're trying to find. So the probability of getting a 10 here, you've got a circle that is pi, the radius is 3 squared, all over the area of the square. So the area of the square is, now this is kind of tricky, you've got 3 plus 3 plus 3, so half of this is 9, making the whole thing 18. So it's an 18 by 18 square, so 18 squared. So you can go ahead and multiply that through, you get 9 pi over 324. And when you calculate that on your calculator, I used the pi button for this, you get 0.087 or 8.7%. So that's a very small probability of getting in that circle. Now they want you to also find the probability. We want to compare that to getting 0 points. Now the 0 points, that doesn't look like it takes up much of that board. So let's figure out the probability of 0. I'm going to erase this. Our total is still the square. So the total is still this square. Now we have to do a little subtraction here. Okay, what we're going to do is for the area of that circle, of outside the circle, so this 0 here, we have to take the box or the square minus the largest circle. So you want to take the box minus largest circle. So we're going to take 18 squared, so the area of the square, minus, now this radius, okay, is of the yellow one, so of the largest circle. So the radius, once again, was 3 plus 3 plus 3, so pi 9 squared was the radius, was 9, and then you still have the total area of 18 squared. Okay, so basically we're taking 324 minus pi 9 squared, and I just plugged that all into my calculator at once, and I got 0.214, which is 21.5%. So the probability of getting 0 points is 21.5%, and the probability of getting in that 10-point range is 8.7, which makes sense. Getting the higher points should be harder to get. So let's answer this question. It says, are you more likely to get 10 points or 0 points? More likely to get 0 points. Okay, Okay, we talked a little bit about experimental and theoretical. Remember, theoretical is the actual probability, like you going through the math of here are the total outcomes that are possible. This is the chance of it happening. Experimental is you actually going through the process, you flipping that coin. Okay, well, how many times do you get heads? How many times do you get tails? How many times do you roll a 6 on a number cube? Okay, how many times when you spin a spinner that you get a certain color? So an experimental is you going through that process. Theoretical is the actual probability of what's there. So it says each section of the spinner shown has the same area. The spinner was spun 20 times. The table shows the results. For which color in the experimental probability of stopping on the color is the same as the theoretical probability? I just want to go back here really quick. Theoretical is the same as experimental in the fact that you have still a total here, but this is the total number of trials, and this is the number of times that it has happened, okay? So same in the fact that you're still taking a total here. So first of all, let's talk about the theoretical. So the probability of red is going to be the same as the probability of green, which is going to be the same as the probability of blue, which is the same as the probability of yellow. And what I say about this is all of these are equal areas, and it says this in the problem, and it all has the possibility, if you take 100% divided by 4 equal parts, you've got a 25% chance in all of these. So this is just the theoretical probability for each color. Okay, the actual probability of it happening. Now for the experimental, okay, you know that you're taking all of these out of a total of 20 spins, and it says that up in our problem here. So they spun it 20 times. Now, based off of the experimental, the probability of red, they got 5 out of the 20 times. Probability of green was 9 out of 20 times. Probability of blue and the probability of yellow was 3 times. So I'll just put those all together in one since you're going to get the same thing. So when you take 5 divided by 20, you should get 25%. And then when you take 9 divided by 20, you get 45%. And then 3 divided by 20 is 15%. So if you look at this, it says which color is the experimental probability of stopping on the color the same as the theoretical? So because it was the same for red, we would say that it would be the same for red. So experimental probability of landing on red is same as theoretical probability. Okay, and last example here. In the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. The type of pets these adults have are shown in the figure. What is the probability that a pet-owning adult chosen at random has a dog? Now, you can believe that on an MCA or on an ACT, they're going to try to mess you up with all of these different numbers. Notice that they gave you 2 survey totals here. There's only one of them that's important. So let's read this question again. It says, the types of pets these adults have are shown in the figure. What is the probability that a pet-owning adult chosen at random has a dog? So we want to find the probability that they have a dog out of the pet owning adults. So we don't want to take out of all of the adults. We want to talk about only the 1,328 of them have at least one pet. That's what makes them pet owning. Okay, so looking at this here, so we've got a dog, a cat, fish, bird. Okay, so of these 1,328, so 1,328 are pet owning. Okay, 916 of them have a dog. So this one, you literally take 916 divided by 1,328, and you should get 0.690 if you round, which is 69%. So that's all based off of the table. You'll have, I'm sure, a lot of these on the MCA and on the ACT as well.